So, let us see how the resonant length it varies with the substrate thickness and epsilon r. So, in this figure we are considering two different epsilon r value. In the left hand side plot, epsilon r equal to 12.8, this is for gallium arsenide substrate, and right hand side epsilon r equal to 2.55, this is for the PTFE substrate. Now, what we are doing, we are calculating the resonant length. So, this is normalized resonant length versus the substrate thickness d by lambda naught. Dotted line, it is for the half wave dipole antenna, and solid line, this is for the rectangular patch antenna. This we have one more black dotted line. It represents the line where it is equal to lambda naught by 2 multiplied by root epsilon r, that is from the thumb rule. Now, if I look at the plot, what we see, with the increasing substrate thickness, which is represented by d, for the rectangular patch antenna, resonating length decreases, and for dipole antenna it increases. Not only that, one more interesting thing we see, this curve for printed patch antenna, it stops at 0.08 lambda naught, that is the limiting case. After that, we can't identify any resonance behavior on patch antenna. Now, the reason is why? Because of the surface wave mode generation. When d by lambda naught is very small, we do not have any surface wave mode as such, but as d increases, we have more and more surface wave mode excitation, mode generation, and power is lost to surface wave. After 0.08 lambda naught, you can say even we can't identify any resonance, patch is not radiating at all, almost all of its power is lost to surface wave. Now, if I decrease epsilon r, what do we expect? At least we can increase this limit. So, in right hand side plot, you see again the same thing, dashed line for half wave dipole and solid blue line for rectangular patch antenna. So, since here epsilon r is 2.55, we could increase it to 0.11 lambda naught, at least the thickness of the substrate d. For dipole antenna, we do not face as such any problem. Of course, there is surface wave mode generation, but even till let us say 0.3 or for lower dielectric constant 0.4 d by lambda naught, we can identify the resonance mode. If you look at this structure, surface wave for left hand side and right hand side, they will be having different characteristics. Why? In left hand side, we do not have any ground plane, simply the dipole, it is printed on a laminate, and right hand side we have rectangular patch below dielectric slab backed by ground plane. So, if I look back to surface wave properties, left hand side, for the left hand side case, we have to consider a dielectric slab simply, and right hand side a dielectric slab backed by ground plane. Now, let us see how bandwidth varies with the thickness of substrate. In general, if we increase the antenna volume, that in that case Q will decrease, this is the radiation Q, QR, and the bandwidth will increase. So, if I increase d, thickness of the substrate, we are increasing the antenna volume, and what we expect, that bandwidth will increase. Look at the plot for two different epsilon r. For epsilon r equal to 12.8, we are considering width of the antennas for both of the antennas is equal to 0.3 lambda naught. Now, for patch antenna, it increases sharply. After 0.08 lambda naught, we can't identify the resonant mode, so we are stopping here. And for dipole antenna, as expected, it is first increasing, but after that it is decreasing. This is due to the surface wave problem. But we have one transition point here near 0.18, again it is increasing. So, this increment is due to radiation from surface wave. This is not for radiation from dipole antenna. Now, you see one thing, if we have surface wave generation inside dielectric slab, what are the problems we can face? Obviously, it is a loss of power or wastage of power into surface wave modes. Now, if the dielectric slab is infinite in xy plane, then surface wave it will propagate along x and y, and the electromagnetic wave it will spread over the surface of the dielectric slab. In that case, from a radiation point of view, we do not have any problem. Only problem is power lost to the substrate, and as a result antenna efficiency will decrease. But in practice, always dielectric slab is finite. We can't use infinite dielectric slab. In that case, what will happen? If we use finite dielectric slab, then we will be having radiation from surface wave, and it comes at the dielectric air boundary. So, this radiation it can be in random direction. We do not have any control over this radiation. Polarization of the electric field it can be in a random orientation. Variation of radiation intensity from the surface wave, that can be also in random direction. As a result, if I look at the radiation characteristics of the antenna, cross pole level will increase and side lobe level will increase, which is not desired. At millimeter wave frequencies, then we have to be very careful not to excite this surface wave. So, next we see the antenna efficiency variation with the substrate thickness. For epsilon r equal to 12.8, it is shown by blue and dashed line for the microstrip patch and half wave dipole. As expected, due to surface wave, they all decreases and their decrement almost have similar value. Now, after 0.11, we are again plotting the efficiency for microstrip patch. So, this radiation or increment in antenna efficiency, it is not due to radiation from the patch, but this is due to the radiation from surface wave. And if you remember, for microstrip line we can't avoid coupling with TM0 mode, and the radiation is mainly coming from the TM0 surface wave mode for patch antennas as well as for the half wave dipole antenna. After this transition, we have one more second transition here. Then for the dipole, power is lost to TE1 surface wave mode, and antenna efficiency again decreases, because for the TE1 surface wave mode we do not have sufficient radiation from the structure. We have similar variation for lower dielectric constant also. So, you see first the antenna efficiency decreases. So, only for this first part which is showing negative slope, we can say radiation is due to the antenna resonance. After that, radiation is mainly from the surface wave modes. So, we can see some observation. For gallium arsenide substrate, almost 50% power is lost to surface wave for d greater than 0.05 lambda naught. You can calculate it. If the substrate thickness is just it's more than 0.05 lambda naught, where lambda naught this is the wavelength in free space, then 50% power is lost for gallium arsenide substrate. Next, we plot efficiency variation versus the substrate thickness for different loss tangent value. If we increase the loss tangent of the dielectric slab, obviously we will be expecting more loss. And if we consider now a thinner substrate and let us say feeding the same power to one rectangular patch antenna. So, for thinner substrate, obviously electric field intensity will be higher inside dielectric and we will be expecting more loss for thinner substrate. This loss is the dielectric loss. So, look at the plot then. When d is small compared to lambda naught, loss increases sharply. This loss is due to the dielectric loss and this is because of the increased electric field intensity value. But if we increase the thickness of the substrate to some point, then the dielectric loss is negligibly small, and as we expect, higher tan delta value is providing higher loss compared to the smaller one. And the effect is more prominent for half wave dipole. Why? If I go back and look at the structure, the half wave dipole, it is radiating in upward direction as well as in bottom side, and it has to radiate through the substrate. So, that is why the effect of dielectric loss is more prominent for dipole antenna. Next, let us say we are going to design some arrays at millimeter wave frequency in printed circuit board technology. Then what are the problems we faced at millimeter wave frequencies? When we design some array, we have to feed the antennas. So, we have to design some feed networks for that, and for the feed networks we use different guiding structure. In PCB form, most popular guiding structure as the feed network is microstrip line. Now, already we know that microstrip line is lossy at higher frequencies. So, obviously loss will increase from the feed network at millimeter wave frequencies, and not only that, we may face also spurious radiation from the feed network, and that will degrade the radiation characteristics of any antenna. Degradation in terms of it can be cross pole level and increased side lobe levels. So, let us see the first example for one. We have an array of two resonating patch antennas. Now, we are feeding it. In the first example, it is using one T network. This solid black dot, it represents the tip of a coaxial probe. So, it is being fed from below the substrate by using one coaxial cable. In the second example, we are calling it without T. We are not using this extension, directly connecting the tip of coaxial cable to this point, and then we are plotting the normalized radiated power versus angle for this particular example. It was designed at 38.6 gigahertz. You see the radiation characteristics, it is significantly different. So, this dotted line, this is without T, and the solid line, this is with T. So, beam width, it changes with T, and this is due to the spurious radiation from just this extension. It is very little, even then we can't neglect the effect of this in the radiation pattern. Let us take some more example. Here one big array antenna you can see, and this line, straight line, they are nothing but feeding microstrip line. We are using one corporate feed network here. It is a 16 by 16 array antenna and designed on 0.254 millimeter thick RT duroid 5880 substrate. So, RT duroid 5880 substrate at 40 gigahertz. its arterioid has a loss tangent of 0.0009 at 40 gigahertz. Now, look at the radiation pattern. Solid line, it represents the copole pattern, and dashed line, it represents the cross pole pattern. What we can see, it is having high cross pole level left hand side and right hand side, and this is due to the spurious radiation from the feed network. So, this feed network is also radiating some power, and for that we do not have any good control over the electric field. So, how we can avoid this then? We have to separate somehow the feed network and the radiating patches. How people do? They will place the radiating patches in one layer and design the feed network in another layer. Then we have to couple power from the feed network to these radiating patches, and for that we can use ground plane aperture, a GPA. So, some slots basically which are etched in the common ground plane of the antenna and feed line structure. Let us see, this is one example. So, this antenna array is designed for 60 gigahertz application. You can see the feed network, and these elements are the radiating patches. These are the square radiating patches, 16 by 16 array on top plane, and in the common ground plane we have slots that is not shown here. So, power is coupled from the feed network to these patches through these slots. And now, look at the radiation pattern, copole and cross pole level. So, cross pole level shown by these dashed lines, they are now much below in comparison to the previous figure. So, we can improve the cross pole level significantly by using separate substrate for the feed network and the radiating patches. Now, when we design at millimeter wave frequencies, we have seen that we have to use a thinner substrate. People are using typically 10 mil or 5 mil substrate for 60 gigahertz application. Since the substrate thickness is very small, it is fragile and mechanically not a rigid structure. We have to use some supporting structure. Usually people use brush plate with that. Then how to design this transition through brush plate from feed network to patch antenna, that becomes another challenge. Let me show you some examples here. How to couple power from the feed network to antenna. We are showing the cross sectional view. We have two substrate. The bottom blue line, it is showing the dielectric slab 1, and this top one, it is dielectric slab 2. You can see the feed network microstrip line, it is designed on the bottommost plane, and topmost plane it can be the radiating patch. In between we have thick brush plate, and now we can design that GPA or ground plane aperture to couple power from microstrip line to patch. It is showing the cross sectional view. Now, bandwidth of this transition, it depends on the slot width, and the slot length is approximately lambda g by 2 at the design frequency. We can improve the bandwidth of this transition by using different shapes of the slot. One such technique is, instead of using one simple line, you use H shaped slot. You will be having higher bandwidth. In this third example, the bottom line, the bottommost microstrip line, it is being directly connected to topmost patch or topmost, let us say we have one more microstrip line by using coaxial, by using via metal pin. So, if you look at the structure, this mid layer, somewhat it is looking like one coaxial cable. So, the brass plate, we have to drill a hole inside the brass plate to insert this metal pin. So, this metal pin, it looks like the inner conductor of a coaxial cable, and the hole which is etched in the brass plate, it looks like the outer conductor of the coaxial cable, and we can model it by a coaxial cable. Here we are showing the simulation result of a transition using ground plane aperture, but the aperture shape is H shape. You can see it is quite good transition, and the operating band is 45 to 55 gigahertz. S11 is almost below minus 15 dB. So, for array design of transition is another important factor. Now, arrays we design for different types of applications. For some application we want very narrow beam, let us say for line of sight communication. In that case, we do not want any radiation in other direction other than the desired direction. So, the beam width should be as narrow as possible, side lobe levels should be as down as possible, and gain should be as high as possible in the desired direction. Now, consider another application. Let us say one transmitter, millimeter wave transmitter, it is placed at one corner of the room, and we want to communicate with different people sitting inside the room. Now, we know Friis transmission law. So, the man who is very close to the transmitter, he will get maximum power, and the man carrying device which is far away from the antenna, he will get much lower power level if I consider uniform radiation pattern. So, we can tailor the radiation pattern for such application, so that the gain will be higher for that longer length and gain is smaller for the shorter length, and the resultant pattern, it is usually we call the cosecant pattern. This is one example of such application. You can see millimeter wave transmitter, it can be even for base station application, it wants to communicate with different devices at varying length, varying distances, and for this type of application, instead of a very narrow beam width, we want a cosecant beam, and we can actually tailor this radiation pattern by changing the power level fed to the array antennas. So, that is a subject of array antenna, and we are not going to that, we are just discussing what are the challenges we face at millimeter wave frequencies. Another example, this is slot antenna in rectangular waveguide. Already we know that rectangular waveguide, it provides minimum loss, and it also have highest power handling capability. So, for many defense applications and space applications, people till now using rectangular waveguide, and we do not have any other choice, other alternative at millimeter wave frequencies even in near future. Then how to design antennas in rectangular waveguide technologies? There are two different categories. One is by using resonant antennas, and the second category traveling wave antennas, we will discuss later. So, for resonant antennas, we have to use some sort of radiator or open structure which will be resonating at the radiating frequencies. The most popular structure is slot, etched on the broad side of a rectangular waveguide. Now, let us say we are etching a slot on the broad side of a rectangular waveguide. If I draw the cross section of one rectangular waveguide, So, where to place the slot? If I place the slot symmetrically about the central axis, then it will not excite the slot. The TE10 mode, if it propagates through the waveguide, it will not excite the slot. Why? Let us see the field configuration of TE10 mode. We have electric field maximum on the central plane and it varies sinusoidally. On the side planes, side walls, it is 0. Now, if I draw a slot here, maybe on an infinite ground plane, I am showing the cross sectional view, then for slot we know the electric field configuration in odd mode excitation, it is like this, and it radiates from this odd mode perpendicular field components. So, if I place a slot on the mid plane, you see the potential difference between these 2 points is 0 simply. So, this field can't excite the slot. In other words, we can say the impedance seen by the slot is infinite. So, if I etch a slot along the central line of any waveguide on the broad walls, even though we are disturbing the current distribution, it will not radiate. That is why in microwave lab, when we use microwave bench, you might have noticed that we use long slot cut just on the central axis, through which we monitor the power inside the rectangular waveguide by using a probe. So, what we have to do then? We have to use some offset to excite the slot. So, that means slot, it is not on central axis, but with some offset. If I change this offset distance, then accordingly the excitation of slot will change. If I place slot more near to side walls, we will have more radiation from the slot, but at the same time it will change the loading of the waveguide. Finally, we have to feed the power to rectangular waveguide over which we are etching the slots. Now, when we place the slot on the central axis, there is no effect on the rectangular waveguiding mode, or you can say in other way that for the feeding port to the rectangular waveguide, there is no change due to the slot. But when we use some sort of offset, then the input impedance changes, and this change is maximum when we place the slot near to side walls. So, then the final placement of slot, this will be a compromise, and because we have two opposite behavior, when we place the slot near side walls, we will see maximum input impedance mismatch, but maximum radiation from the slot. So, let us go back. This is one example of waveguide slot antenna. You can see the slot etched on the broad side of waveguide. Now, if I look at the field components inside slot, we will be having actually Jx component and Jz component of current, and Jz, this is negligibly small, and the radiation it mainly comes from the perpendicular component or Jx component, which is maximum on the central line of a slot. We can use some tilt also as shown in this figure. In that case, radiation it becomes a function of phi, and approximately it can be shown radiated power, it is proportional to sin square phi. When it is perpendicular, very little power is radiated by the slot, almost 0. Now, for the array antenna, we have to repeat this slot structure. In this figure, it is shown such a array antenna. One interesting thing you can see, when we repeat this element, it is in the opposite side of the central line. Now, the question is why? Again, let us go back to basic structure. Now we are considering top view of a rectangular waveguide, so that you can see one broad side. Let us say we are having one resonating slot here, which is on top of the central axis. Now, if I plot the electric field variation inside the slot, obviously it will be having maximum here and minimum on the edges of the slot. Now, inside, if I plot the electric field considering the cross sectional view, we have TE10 mode inside. So, on the central plane we have maximum and on the side walls we have minimum. So, looking at the electric field inside the waveguide, we can say for this slot electric field will be from right to left as shown here. If I etch another slot at the same position, but opposite side of the central line, then what will happen? We have electric field in the same direction, but in this case you see maxima on left hand side, then the electric field it will be from left to right inside the slot. So, if I etch one more slot here, inside the slot electric field will be in opposite direction. Now, if I look from broad side, they cancel each other's effect. So, we have broad side null, but this is the desired direction. So, we can't place a slot like that, it is called slot doublet. Similar problem we will be facing if I place another slot just after this in the same direction. Now, along the propagation direction, here if the electric field is upward, after lambda g by 2 it will be downwards. So, in this figure 1 and figure 2, the direction of electric field will change. So, this slot electric field it will change its direction. So, again we see if I place the slot here with a lambda g by 2 separation between these two, electric field will be in opposite direction. So, we can't again place the slot here. So, the only solution is then we have to etch the slot here, so that electric field in the same direction. Sorry. So, that is how this array is designed. The right hand side figure, it shows the slot etched on the narrow wall. It is not actually an example of a resonant antenna, it is an example of leaky wave antenna. We will discuss it later. Now, at millimeter wave frequencies, fabrication of slot is a problem. Why? Its dimension becomes very small. Then how to drill slot in brass plate? Usually it is done by laser drilling, and we can control the cross section of laser beam. So, when we go for fabrication, the problem we face with laser drilling that we can't achieve, we can obtain this sharp corner of this, you can see the rectangular shape of the slot. So, we have a sharp corner here, we can't fabricate that structure. So, in practice, if I fabricate it at millimeter wave frequencies for 90 gigahertz application or even more than that, then we will be having a rounded structure, and for that if you plot the current density, it will have different distribution. But we have a thumb rule for that. L equivalent, it can be represented by an equivalent rectangular slot whose length can be given by L minus 2 into 4 minus pi by 7 into W, where L is the length of this first slot and W is the width of the slot. Once we have this equivalent length, then we can use all the formula derived for rectangular slot structure. Here is one example of two-dimensional slot array. If we want fan beam, then one-dimensional slot array is sufficient, but if we want pencil-like beam, beam width is narrower in both theta and phi, in that case we have to use two-dimensional array antennas. This is one example of two-dimensional array antennas, and in addition to simple feeding, we have to also use some sort of distribution. So, the power whatever being coupled to these arrays, it will be different for different rectangular waveguide sections, so that we can minimize the side lobe levels. There are some standard technique, one such is called Taylor distribution, and that is being done by using different gaps here, feed lines. So, this is the plot of input impedance S11 in dB, it is for 60 GHz application, and this is the plot of gain. So, for this particular array, slot width is 0.18 millimeter, length 2.56 millimeter, and gain you can see almost 22 dB. This is the measured E plane and H plane radiation pattern. Both of them are showing pencil like beam, and typical radiation efficiency obtained is 68%. It is quite high if I compare with rectangular patch antennas. So, this is the advantage of rectangular waveguiding structure. So, next we will take a break, then we will start on chip antennas.